Hi everyone and welcome back to another lecture. So today we will discuss about vectors, arrays, memories and parameters. Also I will give you a few assignment questions which I will solve in the next lecture. Okay, so let's start with vectors. So what are vectors? Vectors allow you to represent multi-bit values, like which I have used obviously previously, but I have not explained you. Today we will discuss about that. So multi-bit means multiple bits. Okay, multiple bits of rich or net data type. Any data type, it can, like, it is just used for representing multiple bits. That is it. If no bit width is specified, the default value is scalar 1 bit. So if nothing is specified, right, by default it will understand that it is a 1 bit value. Okay, this makes them useful for buses, multi-bit registers and grouped signals. So these are all by default. Reg and var by default are 1 bit values, but now if I specify 7 to 0, that means it is a 8-bit bus with its LSB as 0th bit and MSB as 7th bit. Okay, here this is a 32-bit bus because from 31 to 0, that means 0 is also position, right? That is it, why it is a 32-bit bus with LSB at 0 and MSB at 31. Then I have a vector reg which is 41 bits long, right? What is the difference here? The difference is the LSB is position 40th. Okay, LSB is the position 48 and MSB is the position 0. What is, like, how do I access each bits? So we can write here virtual address, virtual, I will show you in code as well. Virtual address, this 0, that means you are accessing what? You are accessing the MSB. Okay, you can change the MSB bit. Okay, but here the same thing, if I write bus 0, here you are accessing the LSB. So this, right, first number and the last number, the number on the left and number on the right, these define the LSB and MSBs. So this is also very important about defining the LSBs and the MSB. Okay, that you have to understand. And like, you can represent like this bus like this. Bus is a wire which has 8 bits. That means it has 8 wires. It has 8 wires. Okay, so it will start from 0, 1, 2 and it will go until 7. So it will have total of 8-bit bus, because obviously we will not transfer data single bit, we will transfer high bits of data, right? So that's why it is very useful to us. It is a 8-bit bus. Okay, so I hope you have understood this basic thing. We will slowly discuss more about this bit width. So here the same thing is mentioned. The left hand side of this colon will be high, most significant bit, and the right hand side will be the lower bit. Okay, so MSB, the leftmost number in the bracket is the MSB, the rightmost number is the LSB. Okay, as explained here, 040, bit 0 is the MSB, bit 40 is the LSB. We will see it in the code as well. There also we will understand this. Okay, you can see individual bits or groups of bits within a vector. Okay, so bus A7, so I can access the 7th bit of bus A. Bus 20, so I can access groups of bits, right? So access the 3 least significant bits. What it accesses is that basically I am accessing from 0 to 2. That is what I am accessing. Okay, this I am accessing from 0 to 1. But remember the virtual address, right? The MSB starts from 0. Okay, so that means I am accessing the from the MSB, first MSB, then the MSB after that, so on. So these are our MSB and these are LSB. I will show you in a code as well, don't worry about it. Okay, I'll show you in code. So the significant bit must always be on the left in the range declaration. Significant bit meaning the most significant bit. Okay, so basically here, right, in virtual address, if I write something like this 1:0, then it will throw a error in virtual address. Why? Because 1 is not the most significant bit in a virtual address, 0 is the most significant bit. Okay, we'll come to the code, there we will understand. So Verilog provides these kind of part selection as well. I can write like this: starting bit plus minus width. Okay, starting bit plus width, then it will show me the increment from the starting bit and decrement. We will use these notations, like the notations are used here. We'll use this in the code, there we will understand this. Okay, so this is how we declare a vector variable. Let's say this is a 16-bit register. Okay, and this data, 16-bit data, is stored here, assign hex value. Okay, so now if I display, it will display the full vector. Like if I just call it by its own name, like if I write here data and don't provide the bit index, right, then it will store the whole data, whole 16-bit data. Okay, if I would have provided a bit index, then it would have not printed the whole data here, right? It is starting from like this data is printing the whole full vector. This statement is just printing the MSB 15 till 8 vector, and this statement is just printing the LSB 7 till the 0th position. Okay, we will see this in code. Okay, so here again vectors I have. So here if I see initial begin, I'm assigning it a 256 bit number. Okay, so we like, don't worry, if you know a bit about for loop you can understand this, else you can ignore the for loop for now, just understand this line. Okay, what is this line doing? It is accessing a part of the data of data 1 just byte, because each byte is 8 bits long, so I'm accessing 8 bits. Okay, don't have to understand the functionality, just take my word that I'm accessing 8 bits from this data 1. Okay, we'll see this in code as well. So these are few examples I will show you in the code. I will go to the code, there I will show you the examples. Okay, so let's first go to the code, and let me just turn this on VS Code. Again VS Code is not showing. Okay, I have to open this. Yeah, now it shows. So if I have this is the vectors, right? So this is the same code that I have explained to you. So let me just for now comment this one out. Let me just show you this one. Okay, we are only interested in this one. Okay, let me copy and paste this here. Let me do this. Okay, so of course I have changed my location. So again I have to do change directory cd to my current location, current project file location. So I'll go to the current project file location. Current location is this vectors. Now if I do iverilog, the name of the file is vectors, so it should be vectors dot vbp, then vectors testbench, because I am calling the testbench. Okay, then if I press enter, it will compile, no problem. Then I will do vbp vectors dot vbp, correct? So now if I see the output, okay, so what am I doing? So okay, it is actually displaying in hex. Okay, it is displaying in hex only. So hex, right, you can write x also. X is also used for displaying in hex. Okay, so if you see this data 1 is a 16-bit number. Okay, now what is little Indian notation and what is big Indian notation, I will explain that just in a second. I think I don't have any word here. Okay, I will explain that what is little Indian notation and big Indian notation. So if you see the data 1, right, its MSB is 15 and LSB is 0th position. Okay, so now if I store data 1 with this 16-bit number, okay, sorry, my VS Code is again not showing. What is happening? Okay, I'm extremely sorry. I think my VS Code was not showing. So like what I did, this is the code actually. I hope you can see the code. This is the code, and I have just like ran the code. That's it. I'm just ran the code. So if you see that what I'm doing, this data 1 is a 16-bit number. Okay, and data 2 is a 16-bit number, but its MSB here is 15 and its LSB is 0. So now if I write data 1 equals to this number, so it will store this whole number. Okay, and if I print this data 1, I can see the data 1 is 1 2 3 4. Same thing I'm doing, right? Same thing I'm doing. Data 1 is equals to 1 2 3 4, and if I print this data 2, I'm saying I'm getting 1 2 3 4. So although their bit positions are different, but the data that I have stored is same. Why is it so? Because I have told the Verilog internally what is the MSB position, what is the LSB position. That's all. MSB is still the same here. MSB is still 1, LSB is still 4. That is still same. Just the position I have told. So these just decide the position position of MSB and LSB. Okay, that's it. So that's the only thing, that's the only difference between them. So we will come to this. So now if I just like, this is showing what I'm telling it, start from bit 15 and -8, then go till the with 8. Okay, so basically it is displaying, it is a, this is not a 32-bit number, sorry, it will display till 15 till 8. Okay, that is what it is displaying. Start from 15 and go below 8 bits. So it will display till 8, like 15, 14, 13, 12, 11, 10, 9, 8, 8 bits. Okay, so that is what it is displaying, 15 till 8. So if I see 15 till 8, yes, I'm getting the MSB, right? I'm getting the MSB. But here it is doing the same thing, but now it is displaying 0 till 8, 0 till 7, not 8, sorry, 0 till 7. Okay, so what I'm doing, the same data one, I'm displaying 0 plus 8. So basically start from 0 and display till the after, like display till 8. So it will, that's why plus sign is here. So 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, and it will go till the with 8. That's why with 8 is there. Starting bit will be 0 here. Okay, so if you see that if the starting bit is like this, right, what it displays is 3, 4. So the way it will display the number, is like from LSB to MSB only. It will always display the number from it will always display the number from MSB to LSB only. So it displays the number from 7 to 0. Okay, it will always display from MSB to LSB. That's it. It will always do that. Okay, now let's come to the next one. This should be data 2 actually. So this side, if I compile this again, so here if I see, what am I displaying? So I'm starting from bit 15 and I'm displaying till 15 till 7. Okay, 15 till 8. So now if I see what was I expecting, I'm displaying till 15 till 8. And what is like 15 defined? 15 here, right, for data 2 is defined as LSB. 15 is defined as LSB. So I'm displaying LSB. Okay, so this, right, does not display the MSB, this displays the LSB. Here this displayed the MSB. Okay, that's why here MSB is written, but 15 for my data 2 is LSB as mentioned from the position. So 15 minus 8, basically I'm subtracting 8, so I will display till 15 till 8. Again it will start with the highest bit to the lowest bit. So what is the highest bit? Highest bit is the position 8, right? 8 has the highest position out of 15 to 8. Okay, so 8 has the highest position out of 15 to 8. So I will start with 8 and then I will go on till 15. So that's how they are representing. Now I will show you the binary representation as well. This with this you will understand this even better. So let me show you the binary representation. So this is in the hex representation. So I will show you the binary, then also you will understand this better. Okay, this will be percentage %B. Let me copy and paste this. Okay, so let me print this again. Okay, I have not. Okay, you like, that's how we can make the, right? I have not given the variable, right? There are two identifiers, format specifiers, but I have not given it to the variable. I have to give the variable again, right? So you cannot just give the format specifier, you have to give the variable, else it will throw an error. So this is byte, this is byte. So now if I rerun the code, yeah, now it will work. Yeah, so now if you see, now if you observe that this, right, I will write here, this displays like the first line displays still 15 to 8. That is what the first line displays. Okay, So here I can see till 15 to 8 it is displaying. So let me do one thing. Let me display like here the binary as well. It will be easier for us to tally. So again I have to copy and paste this. Okay, not this. This. Okay. So now if I recompile this. Okay, again I forgot to write the data 1 and data 2. Okay, data 2. Yeah, so now it is right. Now if you see that both of them, right, are actually storing the same values. Both of them are storing the same values in binary if I show them. But what is the difference? The difference is it understands what is its MSB and LSB. Like although from here I cannot see, but internally it understands when I try to access the data. When I try to access the data, it internally understands. Generally, 99% of the cases will use this notation. Okay, while MSB will be the highest bit and LSB will be the lowest bit. So this is known as the little endian notation. This I have explained in my COA course. So I will not go too much in depth here. Okay, if you have studied COA, you will understand this. Okay, but sometimes we follow this little big endian notation as well, where my MSB is the 0th bit and LSB is the 15th highest bit. So it will, when I will try to display, right, the binary values, both will be same. Okay, but when I try to access the values, things will change. So let me show you example. So let me access the third bit. Let's say let me access the third bit. Okay, so I want to access the third bit. So if I want to access the third bit, I will just show you this thing. So I will just copy this statement. Okay, third bit of bit of data 1, I will just access one single bit of data 1. We'll see the difference, right? If I'm accessing the same index number, then what am I getting? Okay, bit of data 1 and then bit of data 2. So here it should be data 1. Let me access the data 1 4th bit basically. So let me write here 4. Okay, this means I'm accessing the 4th data 1 bit, and same here only data 2 4. Okay, so everything is fine. Data 2. So let me compile it. Should be compiled. Now we do VVP. So if you see, so bit 1 of 4th bit of data 1, right, is 1, and 4th bit of data 2 is 0. Why is that the case? Because here 4, right, 4 means from the LSB you go to 4. So if I go from the LSB to the 4th bit in this, data 1 is 1, right? So 0, 1, 2, 4 means, okay, no, not the 4, sorry, it is 5th bit, sorry, it is the 5th bit, right? Sorry, I'm sorry. 4 means this is the 0th position, 0, 1, 2, 3, 4. So 4th bit is 1 in this case. Okay, for this, right? So that is what this 4 means in the little endian notation. If I'm going from 15 to 0, so 0 is the LSB, so I go in the 4th. Now what does 4 mean here? Here, right, I'm my MSB is at the 0th position, LSB is at the 15th position. So 4 means starting from 0. So I will start from here now. I will start from here because internally Verilog understand this is my LSB now. That is what Verilog understand. My LSB is bit, this one is my LSB, okay, 15th position. So I will start from here and go till 4th position, 5th position, right? 0, 1, 2, 3 and 4. So the 4th bit here is 0. Okay, 4th bit here is 0. So now I hope you understood the difference between the little endian and big endian notation. Externally, the user will not able to understand this. How the computer stores the data, how in the sequence, that is the internal computer thing. That is not external thing. So ultimately data will be same, just an internal thing. Same thing we are doing here as well. Okay, that here I was displaying bit 15 to 8. So bit 15 to 8 is this one, right? This. So exactly this is getting displayed here if you see. Okay. Now next I'm displaying the last LSB, lowest bits, so it is getting displayed. If you see, this is getting displayed. Okay, but now if I do the same thing, right, copy the same code I have copied, I'm displaying 15 to 8, but 15 to 8 is the LSB in this case. LSB is this one. Okay, this one only. So although it doesn't data 2, this should be LSB. Yeah, fine. So let's just try to understand this, that 15 to 8 is the LSB, because here I have mentioned, right, 15 is the lowest digit value. So I'm starting from the lowest and going to the highest. So it will always like it displays what internally the computer understand, it displays from 8 till 15, because 8 is the highest weightage out of all of this, out of all the values, and 15 is the lowest weightage. Okay, I hope you have understood this point. Now here also the same thing, it will display from 7 to 0. Okay, where it will display from 0, because 0 has the highest weightage, and then 7 has the lowest weightage out of these, right? Starting 8 bits. Okay, this should be starting with starting bit will be 8, starting bit will be 15. Yeah, this is correct. Okay, so I hope you have understood this thing. What is the difference between this little endian and big endian? If you did not, don't worry, ignore this fact, just we will use this one. Okay, we will use this one, that's it. So this I can comment this out for now. Okay, because we are doing something. Okay, so this right can be commented out. Okay, so this one is not that much of use to us right now. Okay, now we are doing something. So this is a for loop. If you don't understand for loop, ignore it for now. We will understand for loop later on. Okay, so what we are doing, basically we are accessing each byte at a time. Then I am adding till, like, what is this doing? For j equal to 0, this will be 0 plus colon 8. That means access the byte from 7 till 0. Then it will access from 15 till 8, because when j will be equals to 1, this will be 8 till 15, basically like that. Okay, then it will access till 16 till 23, like that it will go on. Okay, and this will display the byte, each byte it will display, and this is how I display, right? Display byte 7 till 0. So one thing I wanted to do here before starting, right, if I display it like this, so just wanted to see one thing, that if I can do that or not. So this, right, I'm displaying this data 1, data 2. Okay, so yeah, so what if I wanted to display this data 1 and data 2 like whatever way I have defined it. So if I'm displaying it like this, 0 till 15, if I display it like this, will it throw up an error? No. Okay, still it shows the same thing. Now if I do it like this, 15 till 0, will it allow me to do that? Because my definition was wrong. Yeah, so you cannot do it. Something was in the note, right? I will just pause this. So here, right, I have told you that this one, if you have defined your virtual address to be from 0 to 4, so 0 is the MSB and 40 is the LSB, but you cannot simply access the array, but order has been defined. Order is what? I will go from like LSB, MSB to LSB, right, for 0 to 40. Order has been defined, but you are trying to do what? You are trying to do this 1 to 0. You will not be able to do it. It will throw an error. Okay, that is what I have tried to explain to you. Okay, same thing you can see that I am getting an error here, out of order. Okay, so like even if you do a small thing, right, let's say I'm trying to access from 7 till 0, it will not allow me that. It will not allow me to do that. Okay, but if I try to access 0 till 7, it will allow me, because the order has been fixed. Okay, yeah, the order has been fixed. So like you will understand this more if you play around this code more. like me doing in front of you coding, that is not how you learn, right? That is the honest opinion that I will give you. Once you go and do the coding by yourself, then only you will understand this better. Okay, so highly recommend you to go and like the codes have already been sent to you. Just do the codes by yourself, right? If you just see me doing the code, it will not be of any help, literally any help. Okay, so I hope you have understood the point here. I hope you have understood the point. So that is what I wanted to emphasize on. So now let's comment this one out and let's start this one. Okay, this one should be commented. So now, like as I was explaining, I am accessing the data 8 byte at a time. Okay, and also what I am doing, we can initialize a part of vector as well. If I initialize this part to be 0, that is the clear bits from 15 till 18, right? If this is 1, that means it is still I'm starting from 8 and I'm adding width of 8, that means I'm going from 15 till 8. Okay, so I want to clear it to be 8b0, that means 8 bit number 0, so it will be cleared. And if I just print before clearing, so before clearing I want to print this, and after clearing, before clear, and this is after clear. Okay, so that is the thing. We can clear other bits as well. It is clearing the LSB. Okay, it is clearing the LSB, that also we can do. Okay, after clear. So now if I compile this code, so if you see, like this was my like data 1, data 2. So like here what it is doing is, like as I was explaining, it is showing each byte at a time, because we are adding up bytes, right? So it is doing that. So first byte is the 0th byte, that is the lowest byte, that is the 3 4, because this is a hex number, so each digit is 4 bits. So 4 is the LSB, then 3, so this is the first byte, 8 bits. This is the next byte, right? 1 2, 8 bits. So this is the byte number 1, byte number 2, that is this code is getting executed. Now data before clear is 1 2 3 4. Data 1 after clear, I am clearing the bytes 15 till 8, so the MSBs are getting cleared. MSB 2 bytes has been cleared. Now what I am doing is, again I am initializing the data 1 with the same value, and again I am clearing the LSB now. So the LSB is getting cleared. Okay, the other bits are intact. So we can use this, like this has many use cases. We can clear the LSBs and MSBs like this. Okay, so the vector point I hope has been cleared, crystal clear. I have tried to explain everything. If the little endian, big endian notation is not cleared, still you have to play around with the code. You will understand this more better. Okay, so that's about the vector part. So we have ended the coding part here. So we'll come back. So this is how we use the increment stuff and all those things. Okay, so like I hope you have, like all those things have been cleared to you, how the ordering has been done, how the things has been done. So like these are few applications of vector: representing buses in circuit, grouping control sequence as data bits, handling multiple bits, performing bitwise operations. We understand what are bitwise operations later. Okay, now let's come to another type of data type, that is array. Okay, so if you have studied C, you will obviously like know this, what is array and all those things. So arrays in Verilog allow you to declare and manipulate collection of multiple elements of same data type. So it may seem similar to vector, but remember, vector is just a number with multiple bits. This is not similar to array. Okay, vector is a number with multiple bits. That's it. Vector means not a number, it can be a wire as well, like anything it can be. Okay, vector basically means multiple bits, but it is not same as arrays. Okay, arrays are different, but 1D array and vector sometimes can be interchangeable, but arrays and vectors are different. Okay, arrays can be one-dimensional, multi-dimensional, and are supported for data types such as range, integer, vectors, all those things. Okay, we'll understand this slowly. Array of nets can also be used to connect ports in generated instances. So this is one of the type of array. So in a vector, right, what we used to write, if it's a multiple bit, if my count is of multiple bits, then I would have written count, then I would have shown you the order 7 till 0. But here in array, if it is array, I will just simply define it like this: 0 till 17, 7, right? So this is array, and that previous declaration was for a vector. Okay, so remember, this is the declaration how we declare array. This is a array of 8 integers. This is a array of 8 integers of each of 32 bits. Okay, because each integer has 32 bits by default. So this is a array of 8 integers. Reg bool 31. Each, this is a 32 bit 1 bit register, because it is a reg data type. So I have 32 1 bit registers of name bool. I have 32 1 bit registers. Okay, time checkpoint, again I have how many? 100 1 bit time, sorry, not 1 bit, time is 64 bit, so I have 64 bit 100 64 bit time variables, okay, of checkpoint. Again here, now this is interesting. So what is this port ID? This port ID is array of 8 elements, because it is going till 0 till 7. Array of 8 elements, each are of 5 bits wide, because each are vector of 5 bits. So that's why array means similar data type, right? So it is 8 elements. Port ID is array of 8 elements, each consisting of 5 bits wide. Same is written over here. Array of 6 nets, because this is a wire, each of 8 bits wide. Okay, we'll come to the code, there we'll understand this more. Okay, integer matrix. So like it is a integer array of 2 matrix. It is a 2-dimensional array of type integer. So what are 2-dimensional arrays? If you know this very well, if you know this, if you don't know, I will just explain in brief. So basically 2D array means like what is happening is that this matrix, right, can be displayed like this. Okay, so it has a, let's say, height of going from 0 till 4, that means total height is of 5, and its breadth is going from 0, starting from 0 till 255. So its breadth, right, breadth will be 256. So each, like this will be a like total matrix, like something like this. So each consists a integer element. So each cell has integer element. So what is the length of each cell? Length of each cell, integer has 32 bits, right? So 32 bits. What is the total length of this matrix? So total like size of this matrix. Each cell has 32 bits. Now I have these many rows, like this is known as rows and columns. Okay, so I have 5 rows. So 5 rows into, and each row has how many columns? 256. So into 256. So this will be the total size of the matrix. Okay, so this 2-dimensional array is known as the like rows and columns. Okay, next I have reg, each of 64 bits, and each cell is of 64 bits, but it is a 4D array. Of course I cannot show you 4D array in a like 2D environment, but just try to explain, like this will be rows, columns, then other dimensions will come, right? Then I will go in this backward dimension. Okay, another dimension will come. Okay, I hope you understand the feeling. Okay, so this is the difference between vector and array. Vector is a single element that is n bits wide. Array is multiple elements, each of 1 bit or multiple n bits. Okay, so that is the difference between array and vectors. So example is of reg of 7 bits wide. This example is 7 bits wide, but it is an array of reg. Okay, there are multiple 16 of this reg data type. Okay, so but how can I like access the array or something? I can access array by its index. Like this is known as the index of the array, and this, right, bracket is known as the bit position. Although they are similar, they look similar, but like if you go into the technicalities, then this is known as the bit position of the vector, and this is known as the index of the array. If you have learned C, you will know about this. So this is how we will access 1-dimensional array. I will go into the code, I will explain you, and this is how you access 2-dimensional array. Okay, like writing to an entire array is not allowed. Like in vector, right, we used to do this. We used to write port ID equal to 0, but we will not be able to do that here, because vector is just a single element. but port ID is multiple elements, so other elements can have different values. So I cannot do this port ID equal to 0 and matrix 1 equals to 0. I cannot do this, okay, because matrix is a two-dimensional array. So what I am telling is, in this whole row write all values as 0. That is not allowed. Although it is a, like I'm accessing one of the elements, I'm going inside this one means not this 0th row, in this first row. If I'm going in this first row, it is telling make all of it 0, which is not possible. I can only access each cell in an array. What is allowed is cell. I can access cell, okay, I cannot access the whole row or whole column, okay. So these are all examples of arrays. We can like call nested arrays and all those things. I will not go into the example. This is just a simple like coding example. If you have studied C programming, you will understand this. I will recommend, if you have not already, just search in YouTube C programming arrays. Learn about arrays more, because this is out of the scope of this course. I hope I have already mentioned in the prerequisites that like it would be better if you have studied this, right? So that's why I'm not giving too much emphasis on this, because this is not important for Verilog point of view, okay. So this is how you access the multi-dimensional array, and this is net of arrays, okay. So now I will go to the code, and there I will show you, okay. So everything is changing. So now if I go move on to something else, yeah, it is changing. So now again I will uncomment this thing. This is the array basically. There are so many things. So first let me do the 1D array, okay. So this will be MUT. So let me, so of course I have again changed my file, so I have to do cd, change directory, correct. So if I do cd, because my location has changed to arrays, so I will do cd. Of course I hope this is visible. Why is this not doing cd? Okay, this is in, okay, cd this, okay. Then I will do iverilog, not this, iverilog the name of the vcd file, not the vvp file. So it will be arrays dot vvp, okay. Then I will name the test bench, arrays test bench, okay. Sorry, this one is wrong. This one should be backslash. So this will be arrays test bench, yeah. So it is arrays test bench. Now I will press enter. Okay, something syntax error is there. What is the syntax error? Arrays vvp. Okay, something is wrong. Oh sorry, we have to press /o. Sorry, I missed the /o. That's why like you should not always use the previous commands. /o is there, so make sure you make the /o as well. So vvp, then arrays test bench, okay. And now if I do vvp arrays test bench, arrays vvp, right? So you can see like let us go through the code once. So like this count is an array 1 bit, like each element of this array is 1 bit wide of integer data type, okay. So if I initialize count of 0 to 5 and count of 1 to 5, so now if I access count of 0 and 1, I am able to access count of 0 and 1. But can I access the whole array? Can I access the whole array? No. Like if I write here count, right, in a vector you would have accessed the whole bit, right, all of the bits. But if I write count here and if I try to compile, it will throw out error, okay. It is not throwing out error, okay. But when you try to display, right, it will not display. That is the problem. It will not throw out error, but when you try to display, it will not display. But let's say if I want to access like this, which I was doing in vectors, like this 0 colon 7. Can I do this here, right? It will not throw out an error, okay. Here also it will throw error, that arrays cannot be indexed by a range, vectors cannot. So this is the difference between arrays and vectors. Vectors can be indexed by range, right, because I'm accessing, like it is a single element only, I'm just accessing it bit by bit, okay. So I can access the whole bit. But array is not like a bit, right? Its single element is not a bit. Its single element is an integer data type. Okay, so just be careful about that. So array cannot be accessed through index. So that is the difference that I wanted to discuss. So this is a very basic example. Now let's take a multi-dimension array. Okay, so if I choose a multi-dimension array, again I have to copy the module name because I have to call this module. So this will be MUT. So now if I call this, so multi-dimension array, as I mentioned, like the first one is generally called as rows and second one is columns. So like remember, if you write the sequence here, right, then this is the highest value, this is the lowest value. So just be careful about the sequence, okay, how you remember the sequence, but it doesn't matter that much. But generally try to follow this sequence only, 2 colon 0. That is the best way. Like this is the highest location of the array, this is the lowest location of the array. That is what we generally follow, and follow that. Don't use this confusing thing, okay. This is just for the example sake, that's why I'm showing you this. So here in the 0th row, 0th column, I'm storing the value 1 because each element inside this matrix array is 1 bit wide. So each element of array is not 1 bit, sorry, 32 bits wide. Okay, each element is 32 bits as I'm initializing it with 1. So because like all the other bits are 0 on the left hand side, so that's why you will see 1 only here. If you see, you will see 1. Now if I access the 0 1, you will see 2 because I'm initializing it with 2, and like other things as well you can see. Okay, so yeah, just this is a key point. Each element in the array is 32 bits wide. Okay, but you cannot access it like vectors. That is one problem. You cannot access it like vectors. So let's say it is 32 bits wide, right? And if I store, let's say, a 32-bit number, okay, like a 32-bit number, so anything I can store, 1024, something like that. Now let's say like it is a 32-bit number, right? So in like same thing I will do. I will define an integer vector data type, integer vec, and it is a 32-bit wide integer. Okay, so like I will do the same thing only. Vec will be equals to 32 d12 1024. Okay, now if I try to, like, I will do the same thing here. So I will do vec. I will tell the 5th bit of vec. This will be percentage 0b. This is the last one. So if I show the last one, vec 4, because like I'm starting from 0, so that's why the 5th bit will be at the position 4. So now if I try to show the 5th bit of this matrix 0 0 as well, right? It is a 32-bit number, so I should be like, if I write here 5 4, I should be able to access the 5th bit. So but will I be able to do that? It shows a syntax error. Okay, one mistake I was doing, that like integer has already like fixed 32 bits of data type. I cannot like tell a integer to be of 32 bit. So I have to initialize this with reg. Okay, reg of 32 bits. Okay, that is what I was making the mistake. So now if I compile this, it compiles, right? Without any error, it compiles. Now if I try to access the 5th position bit, okay, will it compile? That is the interesting part. It still compiles. So if I do VBP, okay, it actually shows me that it is 0. So actually there is no problem, we can access it. So there is no problem, we can access the 4th bit of integer as well. There is no problem. So like you can explore. Of course I also don't know everything, right? I also try to explore in the code and understand what is like possible and what is not possible. So we can access bit by bit as well. Okay, let me write this as a reg only of 32 bits. Okay, and then try to access it by bit by bit. Will I be able to access it? Okay, 32 bit Okay, this should be colon, right? So now if I compile it, yes, it will compile, no problems, it will give you the fifth bit. So we can do it. This is possible. Even if it's integer type, then also it is possible. So I'll still make it integer because that will clear the confusion more. So it is still possible. We can access bit by bit in arrays as well, because each integer, like each element is just an integer, and integer are accessible by as a bit by bit. So we can do that in Verilog. We can do that. So I hope you have understood this thing. How can I access? So now I will comment this thing out and uncomment this one. Okay, 4D array example. This, right, you can ignore, like this is just a nested loop example, that's it. Okay, so 4D array example, this I'm not interested in that much because like not that important. So mut, so now if I do iVerilog vpp, okay, so what we are doing basically is that, like, this for loop, right, is just nested for loop. If you don't know what is nested for loop, just search in YouTube nested for loop, you'll understand. Okay, so what we are doing is, first I'm going inside this I, then going inside this j, then k, then l. So because I need 4 numbers, right, to access a 4-dimensional array. This is a 4D array, and each 4D array, each element of array has 16 bits. Okay, because each element is 16 bits wide, as you can see from the code itself, right? So I can, like, what am I doing here? I'm initializing all the array elements to be 0. Like, I'm going in the loop and I'm initializing all the array elements to be 0. I will not explain the code because like that will just waste another time. I don't want to go and explain the code right now. Okay, so then I'm doing what? I'm assigning a specific value to a specific element of the array, like the array 1 2 0 5, like first row, second column. But then what dimensions you can say, like this is, I cannot comment about names of these dimensions, right? So we're assigning 16-bit value because it is allowed. But if I try to assign a 32-bit value, right, if I try to assign a 32-bit value, it will not allow us. Okay, here it is allowing, but because it is 0. Okay, no, it will allow us. It will just truncate. It will just truncate the 16 bits. Okay, that is what it will do. So just be careful about this. Just be careful about these things. Okay. So if you want to display all the arrays, you can copy the same code. Okay. If you copy the same code, you can display all the arrays. Okay. What I will do, I will press here display, $display. Okay. Don't have to understand the code right now. Do a bit of digging by yourself, because if I spoon feed you everything, you will not learn anything. Okay, so array elements. Okay, so there are so many array elements, like huge array elements. This will show all the array elements. Percentage d comma this, and then semicolon. So this right, what it will do is it will access all the array elements. That's it. Okay, that's it. Don't have to understand this code right now. Like, just search on YouTube nested loops, for loops. You will understand what am I doing here. Okay, so now if I try to print this, right, it will print. It will print how many? Just this one. If you want to print like what exact element is it is changing, so we can print the element as well. So it will be array. So what I can do, right, I can cut this and I can exactly print what element it is printing. So it will be percentage d. This d will be the placeholder for I. Okay, I want to show the indexes as well, right? So I want to show the indexes, so I will show the indexes. So this will be 0. Then I have to copy this thing again 4 times, paste, paste, paste. Now what I will do, I will show you I, j, k, L. This also I will show. Okay, so this will be, okay, this is not correct. This, now if you see, like, it will show all the elements. Like, what the for loop is doing is, right, first it is like it is fixing this one, then it will change the last element always. 0 for 0 0 0, the last element will go from 0 till 7. Okay, then again this will reset, and then this element will go to 0 to 1. Then again all the previous 3 bits will be fixed. I'll go till 0 till 7, again this will change to 2, and then again it will show all the elements. Okay, so that's how you can display the array elements as well. I hope you understood this point. Like basic code, this is for loop. I am not explaining for now because we have a lot of things to learn. So if we start here, net array example. Okay, so this is the same thing, only just instead of a reg data type or integer data type, it is array of 6 net data type. So like of course we don't need to show it to you. Now let me show you the last element, last module of the arrays, this one. So here I have everything like integers, multiple bit arrays, then I'm displaying displaying one dimensional arrays, accessing multi-dimensional arrays, and writing the entire array is not allowed in Verilog. It will show error. So I will show you that as well, that it is not allowed. Okay, I will show you that as well. It will show array cannot be indexed by an integer. Okay, so like all this, I hope you know how to access the one dimensional array. So slowly I will show you. Let us first do the first part. Okay, accessing one dimensional array. We have already done this, but still I wanted to repeat this thing again. So let's do this once more. So if I try to compile this, okay, mut, okay, this I have to comment out because twice I cannot instantiate the same name, same module name, right? So that's why it was throwing error. So if you see, like as it is an integer data type and initial value of integer is x, right? So that's why if I try to like I have initialized the fifth element of the array to be 0, but I have not initialized any other element. So if I try to access any other element, it will show x. Okay, that is the only thing that I wanted to show you because it is an integer data type. Okay, so this is done. Now if I try to access multi-dimensional array, this has already been shown to you. If I try to access multi-dimensional array, you can see the multi-dimensional array. So now if I again try to compile this, you can see that this I can do. This is allowed, right? This is what? This is vector. The last bit is the vector. 4-dimensional is finished here. 4-dimensional array is finished here. Okay. After this is vector. So this is allowed. Accessing by range. But this is not allowed, right? If I try to do 7:0, it will throw out an error. This is not allowed. Okay. So like if I try to compile this code, right, it will show me that array cannot be indexed by integer. So I cannot index array, but I can index by range vectors. That is allowed. So I hope you have understood this point. So like this is what it is showing. So as I have initialized the matrix 1 0 to be this digit, it is a 2-dimensional array. That is fine. But for the 4D array, right, I have initialized the first 16 bits of the 0th element, okay, as 1 1. But the next 16 bits, right, I have not initialized. Simply it is x. Simply it is x. Okay. So now let's do the next assignment. This illegal operator. Okay. So if I try to uncomment this thing. So first of all, this is anyways not allowed. This thing is not allowed. Okay. So let me comment each one at a time. So this one is not allowed. Port, like I'm initializing the whole array to be 0. Port ID. Port ID is an array of 8 elements, each of 5 bits wide. I cannot do this. This is not allowed. Okay. It will say entire array to slice. It requires system Verilog, which is like high level stuff, which is not in our syllabus. Okay. So we will in Verilog we won't be able to do this. Okay. This also we won't be able to do. Matrix 1. Matrix is a 2-dimensional array, right? I am telling that make the whole row to be 0. Matrix 1 is a where did it go? It is a 2-dimensional array. I am telling the make the row 1 to be 0. This is also not allowed. It will throw a error. Okay. Now if I try to display it by range, again the same thing we already know that arrays cannot be displayed with range. Again, it is not allowed. Okay. So if I comment this one out, and then the code will totally compile, no problems, error free. Okay. So I hope you have understood the arrays. So we have gone very in depth of the arrays as well. Few things I have not explained, like the for loop, all those things, because I am expecting that prerequisites you have done. Okay. And if you have not done, you can do it now. Okay. Before watching this video, you can do it now, and it will not take you much time. For loop is not that difficult. Okay. So let me come back to my writing pad. So where is arrays? Yeah, so this is what we want to learn about arrays. What are arrays used for? State machines in FSM and all those things. It is used for bus implementation, same as vector, but where similar type of data type is being used, right? We use arrays. Memory modeling is very important thing that we use arrays for. In the next topic itself, we'll understand memory modeling and for sometimes storing results and something. Okay, so these are the use case of arrays. Now I will come to the next topic, that is memories. We learn about memories. So memories in Verilog are modeled using one-dimensional arrays of registers. Okay, so that is what memories in Verilog are modeled are. Okay, so what are memories? I will explain those as we move along. So they are commonly used to simulate register files, RAMs, ROMs in digital circuits. So if you have studied COA from me, there I have explained what is a memory, how is memory organized. Okay, the size of each word and the total number of words in the memory determine the memory structure. Okay, so we will see how memory is written, right? So here one example is there, reg mem 1 bit. So it is basically memory each of 1 bit wide, memory of 1 bit wide. So very simple. Okay, so basically what is happening, memory is like this is the 0th memory and each cell is 1 bit wide, so I can store only 1 bit in each cell. Okay, and then I will go till next, so this will be 1, this will be 2, and this will go on till 1023. So total I will have 1024 cells. Okay, total I will have 1024 cells. Okay, then I have multi-bit word memory. So what it means is that each cell, right now the difference is each cell now, although like it is totally 1024 cells, it has 1024 cells, but each cell now has 8 bits, because from this, right, from this we can understand it is 8 bits wide. Okay, so this is a array. Okay, this is a array, but array of what? Array of 8 bits wide. Each element is 8 bits wide. So now I hope you understand the use case of array. Now this, right, fetching a specified word. So here if you want to fetch a specified word, we can directly fetch it with the index of the array. That's just like that. So if I write here mem byte 511, that means it fetches the word 8-bit word, 8-bit value, because each element is 8 bits wide. So it will totally fetch the 8-bit. Okay, we can access by index as well. So basically in this 8-bit, right, each are 8 bits, so they are divided in smaller sections. So each section is 1 bit wide. Totally how many sections I have? 8 bits. So total how much space is it like consuming? I have 1024 rows and each row is 8 bits wide. So this will be 1024 into 8 bits, or I can directly write, because I know 1 byte is 8 bit, so I can directly write is it has 1024 bytes. So the memory is 1024 bytes according to this notation. Okay, so we'll go to the code, there we'll understand this. So this is how you write to the memory location, similar to array writing, nothing special here. So reading from the memory location, again similar thing only. So we can use loops. Don't worry, I will come to loops later on, but basic thing you can understand, like this is a very simple for loop. We are using a very simple for loop. Just I'm accessing, I'm initializing all the values of the mem byte to be 0. So for I equal to 0, it will go mem byte 0 equals to 0. Then it will go for, it will increment by 1, so it will be mem byte 1 equals to 0, mem byte 2 equals to 0. It will go on and initialize all the memory locations to be 0. That's the only thing that the memories will do. So now I will go to the code and explain you the memories portion. So let me just display the code, and I hope it will show. So memories is showing. Okay, so memory, let me uncomment this one out. So there are so many things in memory. So this is a 1-bit memory as I explained. Okay, so let me just I have to do CD again because the file has changed. So again I have to do CD. So if I do CD, I have to copy the location CD, and then I have to compile this again, right? So this is the first 1-bit memory, MUT. Okay, so now if I have to compile this, so it will be I Verilog. Okay, this is going here, I Verilog dash O. Now the name of the VBB file, okay, it will be memories. I can name this anything, memories dot VBP. Then the file that I want to compile the test bench. Test bench is simulating, okay. So memories underscore testbench dot v, okay. Then I will press enter, it will compile, no problems. Then I will write here VBP to see the output, memories dot VBP, because the output is stored in the VBP only, okay. So output here, like what does this code does is, like, basically it initializes the 0th bit, right, the address 0. So like if I want to go back here, right, one thing I forgot to mention is, like, if you want to model memory, so this is known as the 0th address, okay. For a memory, this is known as the first address, second address. So obviously memory will have its address and data, okay. So this is the address of the memory and this is the data of the memory, okay. So these basic memory organization I have explained in the ROM RAM. I hope you have watched that video, okay. So that's why I'm not giving too much emphasis here. So let me go back to the code. So in the code, again, like I am making the 0th address to be 1. So it makes the 0th address of the memory to be 1. Then it makes the last address of the memory to be 0. Okay. If I try to print any other value, right, it will just simply give me x, because reg has initial data type, initial value of x. Okay, so it simply gives me x. So we will obviously not do that. We'll print the last location. Okay, so this is simple 1-bit memory. Let us go to the 1-byte memory. Okay. Okay, so now if I recompile this, so now if I see that here what we're doing is that this is rich membyte 0 till 1023. Okay, so this is a like byte memory, right, and this is just the data, 1 byte of data, 7 till 0, that means it is 8 bits, that means 1 byte of data. So what I am doing is membyte 0, I am storing the 0th address with 8 bits of data, that is AA. Okay, so 8 writing hexadecimal AA, that is it is 8 bits of data. This is 8 bits of data or 1 byte, okay, because 8 bit is equals to 1 byte. Okay, that is what I am doing. Same thing I am doing at the last memory, not last, at the 511 memory location, address location. I am writing FF. Okay, so I am just teaching you the modeling. We are not using the memory, but this is how in Verilog we model the memory. Okay, so 511 and the data is membyte 511. Okay, so this is what I am doing is I am reading from the memory now. This is read value from the address 511. Okay, so in the address 511 FF is stored, that's why it will display the FF. So I'm like displaying the mem byte 0 value, that is AA, and I'm displaying the like 511 value, that is FF, which is exactly what we expected. So that's how we read from the memory. This is the address and the data will be after accessing the address. Okay, this is by the data. Okay, so I hope you have understood a simple byte memory explanation. So like this is just a simple example for initializing the memory, right? All the values will be initialized to 0. Okay, so if I try to show this initialize memory, so initially memory should be x, but as I am initializing it, so all the initial values of memory will become 0. Okay, so okay, something has gone wrong. Okay, sorry, we are not initializing with 0. What we are doing it, we are initializing with that current address value, each word with its address value. So we are initializing each address with its address value. So if I am at memory location 1, so data should be 1, which is correct. If I am at memory location 0, data should be 0, which is correct. If I am at memory location 255, data should be FF. So in hex 255, in decimal in hex is FF. Let's say if I want to store 254, the data should be FE, okay, in hex. So it is absolutely okay, it is not showing. Why it is not correct? It should be 254. Yeah, it is FE, right? It is FE. Yeah, so it is FE, so which is absolutely correct. So I hope you have understood this point. So like this is how we initialize any memory with for loops. Basic for loop, I hope you will search and look it up, you will know. Okay, so this is how we initialize memory. Let's now load values to the memory. How we load values to the memory? Let me show this, how we're loading the value to the memory. This is one interesting fact, is that so we can load any value to the memory, right, from a text file. Okay, so like the load memory is already here, so we can load any value to memory from the text file. So I'll just show you the text file. Text file should be formatted properly, else it will not show you. So let me, if I can somehow show you the text file as well. Okay, so I will open it in Verilog only. Okay, that will be best. I will open it in Verilog only. So not Verilog, sorry, VS Code only. So this is the text file. Okay, the text file is this. Like I can add comments in the text file. It will compiler Verilog will just ignore. So if 6323 is there, right? Just 6 lines of code, 6 lines are there. That means six locations are there. Okay. So now what I am doing is, this is a 8-bit 256 bytes of memory, but I am only storing 6 bits. So we can see how it will store. So how we can read from the memory? So this is the command read memh. Okay, so what it does, it loads the binary data from a file. Okay, so this I can delete, just doing the same thing only. So memory will be loaded. If like it compiles correctly, memory will be loaded. Now if I want to show, right, it will show. So it will display. So let me compile this code. So if you see that here in the text file, the 0th, like the first number was 23. So 0th position has been stored with 23. The second number was 63. So it has been stored with 63. But the 10th, right, I haven't provided it with 10 numbers, like 9 numbers, sorry, 11 numbers, right? I have only provided it with only 6 numbers. So until 5 mem byte 5, it will show the last number. Then it will just show XX because I haven't provided. So it will not get initialized. Okay, so that is how you can load from a memory. Okay, I hope you have understood this point, how we can load from a memory file, text file. Okay, so this is also another interesting thing that you can do. Okay, so whatever we have done, right, the same thing it is doing here. Like you can quickly go through this module memories, the same thing, nothing else. Like whatever we learned, summary is inside this module. So so like here what we are doing, just we are initializing some res bytes, multi-bit memory, then we are displaying something. This we can display mem bytes. This can be displayed. This can be like you can use for loop. So whatever we have learned, right? Whatever we have learned, this is doing the same thing here. Okay, whatever we have learned, it is doing that. So you can initialize that and see. Just you can play around with this. What is this code doing? I will not explain this code because like whatever we have learned, that is like the conclusion. This whole module is the conclusion of whatever we learned previously. So just play around with these numbers and values. You will understand about these memories more. Okay, so I will not explain this code. This is for you homework. Okay, so that's basically it about the memories. Let me go back to my writing pad. So I hope you have understood a lot about memories. We have understood the memories. So like these are the codes. So I hope now you understand each of the codes. Okay, each of the codes, whatever I explained. So Verilog can represent RAM and ROM using write read logic. So, like you can implement in code, right? You can model it. So I'm not modeling it right now. That will be one of your project. Your project will be, one of the project can be modeling of RAM or ROM. Okay, so very basic project, but that you can add on your CV. Okay, modeling RAM, ROM, and like you can go to the advanced topics as well. Okay, then it's register files and all these things, application of memories. These are all the things that memories can do. So yeah, I hope you have understood this thing. Now we will come to the last few topics, that is parameters and compiler derivatives. What are parameters? Parameters in Verilog are constants that allow modules to be customized at compile time without modifying the module's definition. What do I mean? Of course, I will give you a few example. There will understand. So here, right, this is the parameter syntax, how you can define the parameter, and these are the examples of using the parameter. So let's go to the code, and on the code itself we'll understand what does a parameter do. Okay, so I will just show you the code. So let me cross the previous things. If I cross out the previous things, now this is what a parameter is. Okay, so let me just uncomment few things. Let me first uncomment few things. This memory empty will not be here actually. Yeah. This can be deleted. So what we are doing is, so memory hashtag this. So for now I will just comment this one out. I will write memory. Okay, we can change the parameter values, and if I write mem instance, memory mut. Okay, so this sorry, module parameters, this is not memory, this is module parameters, so parameter should be here. So like what we do, right, is we can actually define parameters, this parameter port id. That means inside this module, right, if I ever access port id, it will be always equals to 5. It will be always equals to 5. If I now, like this display statement is here, right, I can display this. So let me run this code. Then again I have changed my location, so I have to do cd. So I will do cd location, then I have to again do I verilog, compile the code, o equals to parameters dot vbp, then I have to do dot parameters test bench, because I am compiling the test bench dot v. Okay, so now we have done this, right? Now we have compiled it. Now I want to display the result, so I will do vbp and display the vbp file, parameters vbp. Okay, so if you see, like the port id, like it is looking like, sir, we are just doing like this is just like a reg variable, right? I can do reg here. Why? What is the like what is the use case of parameter? What is the use case of parameter? The use case of parameter is that you cannot change the parameter values inside the module. So now if I have defined the parameter to be port id 5, right, if I try to change it, you will not be able to change the parameter. Okay, so here let's say if I write here in some initial block, initial begin end. Okay, so port id, if I try to change it to 4, let's say, it will throw error. Okay, it will throw error because there is no variable named port id. It will not be able to find a port id variable. Okay, it can print the variable. I can use it. How I can use it? So let's say I want to make anything. Okay, I want to make anything. It is not a variable. Parameter is not a variable. Okay, I cannot change it. So what you can do here is, let's say I want to make any array of size, like the size of the port id. Okay, or let's say cache line width, right? This cache line width is there. Let's say I want to make a variable, let's say reg, whose width is equal to my cache line width. So I will write here this cache line width -1, because obviously one extra bit is always get added to my dummy variable, dummy memory variable. Okay, so this is allowed. Okay, first of all I have to comment this one out. This is totally allowed. So that is the use case, because once you define the parameter cache width length, because if you write here number, right, 256, there might be a typo somewhere. There might be a typo. You might, by mistake, you might write here 255. Okay, you will not be able to, the code will not be readable. So that's why I make it cache width line. Now it is totally readable. Now when other user will see that this code, right, you will understand, okay, this dummy variable is registered data type whose width is equals to cache width. Okay, cache line width. So that's the use case of this parameter. And another use case is, of course, you will not be able to change this value. you will not be able to, there you can change this value if you want. There is a special syntax, we can change this value, but simply you cannot change it like this. We have to follow some other syntax. Okay, that I will explain. So now the cache width line is currently 256, but there is a flexibility that, let's say, if I want to, while defining the module, if I want to change the parameter, while defining the module, if I want to change the parameter, so I can do it. That is allowed. So if I write now, call it, it should be parameters actually. Okay. So this, right, this will not be changeable. So if I write here parameters, and if I try to change it, now I don't provide the user the flexibility to change the parameter values. So it will throw error. Okay, not found, parameter not found, address with data width. Okay, address with data. Okay, this is the different parameter, right? Sorry. If I write here, okay, let me just change this a bit. This, right? If I want to change the parameter values here, let me copy this and let me do parameters hash dot, the one of the parameter was cache line, right? Cache line width. If I want to change the cache line width to be equals to 32 bits wide, is it allowed? I also don't know, I have to check. So yeah, it is allowed actually, we can do it. So cache line width has now changed. So if I now print the output, right, so you can see the cache line width has changed to 32. So like that's the flexibility of parameters. That is the next topic basically. That is the flexibility of parameters, that you can simply change the cache line width. Okay, there is no problem with the changing the cache line width. Like you have like initially when you are making the parameters, that there was one parameter named cache line width. For this module it was 256 bits long. But later on you understood, okay, maybe the cache line width for this particular module, right, for other module it should be 32 bits. So you can change the parameters using this syntax, this syntax. Okay, that is how you can change the parameters. So that is the next module basically. The next module is this one only. Okay, this one, next module is this one. Okay, the data out and data in is not defined, so somewhere I have to define the data out and data in. Just hold on. So this I can comment out for now. Parameter values are constant and cannot be changed like this. There is other way to change the parameter value, I will discuss about that. So here this is the memory model, right? Yes, this is the memory model. So you can define your parameters like this as well. You can do a hash after naming the model, and then you can define parameter this here. Okay, this is how also you can define the parameter, or you can define the parameter like this as well. There is total flexibility how you want to define the parameter. Okay, so now if I move on to the this code, right, because data width and data out, these are all output input. So somewhere I have to mention this, right? I have to initialize these values. So where data out, data in, address, these are all, yeah, wheres only, so that is fine. So now if I, okay, still invalid module name, what is 14, okay, memory, okay, should be fine. Invalid module name. Okay, sorry, again, like this is a common error, I forget to write the semicolon. So yeah, so now if you see, like what we're doing, we're setting the data width to be 32, address width to be 12 bits. Okay, so here they're doing the same thing, right? So they are defining a reg whose width is of 32 bits wide. So even though it was set here 8, but as I have set here 32, it will set 32. So that is the flexibility that we provide. Although inside this model you cannot change, but while defining the memory instance you can do it, because the user may want to change while defining the model. Okay, so but I only, like, although this is of 32 bits wide, but I am only setting the first 8 bits, setting LSB 8 bits. Okay, so that's why you observe just like the 4-bit, this is written in hex, just the 4-bit are shown. Okay, 8 bits are shown, other all bits are initialized with x because it is a reg data type and default value is x. I'm not initializing the other 8 bits. Okay, so I hope you have understood this point. This data begin, initial, all those things are done. So this is the display statement, so I'm displaying, that's it. So I don't think there is much like confusion about this thing. And data width I'm printing. Okay, so you can print the address width as well. So now how you can override, okay, let's open the setting, how you can override the parameters. So here you can override the parameters. So this is here only. So the same thing. Okay, I think this should not be here. Ordered parameter is next here. So look, with local params you can define and cannot be modified externally. So we will understand that as well, don't worry. I think, yeah, this is the next one, local parameters. So this, right, if I just uncomment this again, because few things I think I have to show you. So you can access the parameter in ordered way as well. Okay, how can I access it? Like this, you can access the parameter in ordered way as well. If you write 16 and 8, right, so in whatever order you have written, like first is data width, then is address width, it will access with the order. If you want to access unordered, then you will use this syntax. If you want to access ordered, you will use this syntax. Here you don't have to write the name of the parameter, just simply write 16 and 8. Verilog automatically maps. So the first parameter here was defined as data width, so data width will be 16, and the next parameter is the address width, so address width will be 8. So let me compile this code. If I compile this code, you can see that data width is 16 as expected, and again, like this has become a 16-bit data now, and the last 16 bits are all, what do you call, last 16 bits are all x unknown, and the last 16 bits are, no, not 16, sorry, first 8 bits are MSB, 8 bits are x, and the last 8 bits are values that has been set. Okay, so this is how you can access in ordered parameters, right? But what about the local parameter? Local param, what is local param? So we'll understand the local param now. So we'll understand with the ALU example. Okay, so this I have to delete. So now few parameters are local here, local param state 1, state 2, this, right? So local params, basically it is written over here, local param is used to define parameters whose values cannot be modified externally. These are useful for constant that must remain fixed within the model. Within the model it must remain fixed, the user should not have any flexibility to change this. If you want something like that, then you will define it as local param. You cannot change the local param. Okay, you cannot change the local param. So here, so one thing I forgot to mention, like I will go back to this previous thing, not this thing, I will comment this on for now, this one also I will comment out for now. Let me go back here. So as I was telling, right, this let me uncomment the first one. Okay, uncomment the first one. So as I was telling, okay, something, this one should be only uncommented. Yeah, so if I uncomment the first one, like I haven't told you how you can modify the parameter within a like module, how we can do that. So you can write this def param statement. Okay, so if I write def param, okay, and write port 0, then it will not throw out any error. Okay, it will not throw out any error. So now if you see, it has changed, but this is not so I will what I will do, I will copy this, delete this. Parameter values are constant and cannot be changed. So parameter values, parameter values can be changed with the keyword def param, but not recommended. We don't recommend using this because then the point of the parameter changes, right? It should remain constant within the module, it should not change, but not recommended. Okay, just be careful about this thing. You can change the parameter value in while instantiating the module. Okay, don't do it here, don't do it here. This will obviously throw out an error, we cannot do it anyways, but you can use a special keyword named def param, and you can change it to port id equals to 4, but that is not recommended. Okay, that is not how you use your def param what. Okay, so yeah, that's basically what I wanted to mention in this first module. Okay, so let us go to the last module, that is ALU. So if I go to the ALU now, okay, so these are all local param, state 1, state 0, state 0 2, that should not be fixed, that should not be changed. Okay, so what it is doing, just it is checking if any of the input changes, like input output changes, it will just see the opcode, what is my opcode, the input, and according to that it will do some output. If it is state 1, like state 1 means, like if opcode is state 1, that is 1, then it will perform addition. If opcode is state 2, that is 2, then it will perform subtraction. It is state 3, then it will perform AND operation. State 4, it will perform OR operation. Okay, depending on the opcode value. So I am here giving some different opcode values. Yeah, currently the opcode value is 2. Okay, so it should perform subtraction, and the inputs are A, B are 3 and 2. Okay, so now if I run this code, okay, I have to close this. Now if I compile this code and see the output, so result is 1, that is subtraction, 3 minus 2, as expected. Like, but what is the happening with the parameters? So the parameter width here is 8. Okay, this is the width of the result. So let's say I am using a bigger number, right? Bigger number. It is currently 8 bits wide, that is what I am setting. But here, right, I have set it to 16 bit wide. 16 bit wide. So let's say if I store a higher bit number, okay, let's say a 32 bit number, okay, 32 hex, it should be 3, 4, 5, 6, but it will not be able to show me 32 bit number. Okay, that is the problem. And this also, let me write this 2 only, that is not a problem. It will not be able to show the subtraction. Okay, so if the result, right, result I want to show in hex, it is showing in hex only. Okay, so now if I print this, if you see that, okay, it is showing it correctly. Is this not okay? This is still, I think this is still lower than 32 bit. If I give it some, okay, this is only 16 bits. This is only 16 bits. Now if I give it, like, if I give it something X, right, 7, if I give it 7, it will not be able to show the correct answer. Here if you see, it is not showing the correct answer. Simply what it is doing, it is just truncating the first three, and just taking the last 4 digits, that is 4, 5, 6, 7, and then subtracting 2. That is what it is doing, right? So that is the problem of your ALU. So now you want to customize, you want to make your ALU to support 32-bit operation as well. So now I will just change this, and I don't have to change anything in this code. Automatically everything will be fixed. Okay, I don't have to change anything in this code. Automatically everything will be fixed. See, that is the power of parameters. Okay, just by changing this, everything, my module now supports 32 bits. That is the power of parameters. Okay, now I have told you, right, this is the parameter thing, the customized parameter. Now I have told you the few local param I should not be able to change it. So now if I want to access this local param from here, right, I will not be able to access it. So let's say I want to change dot state 1, okay, whatever the name of this parameter is, state 1, and I want to make it 4B1000. Okay, but that is not allowed. We will not be able to do it. Okay, if I run this code, it will throw out an error. Cannot override local param state 1. So we that is not allowed. So few things should be fixed in the module, few things the user should be able to customize. So that's why this side we cannot edit the local param. So sometimes you want that flexibility, that the user should not be able to override this. That's why the error, we cannot edit the local param. Okay, so I hope you have understood this thing. Okay, so I will copy and paste this as well, so that this is also there for you to understand. So okay, So I hope you have understood this local param thing that we will not be able to edit, and I hope you understand the use case for parameters. Okay, it is a very powerful tool. Inside this as well, you cannot change the local param. Okay, if I try to change this here, let's say if I try anywhere, right, let's say somewhere here, initial, begin, end, initial, begin, end. Now if I try to change this, let's say def param state 1 equals to 4b1000. Okay, let's see. I also don't know if it will allow me to change or not. So let's see this. Okay, again it does not allow. So basically, right, this local param you can never change it. Local param means you can only initialize it once. You can never change it. Okay, even if I'm using def param, still I cannot change it. Okay, it can never be changed. Okay, you can never change local parameters. Okay, so let's come back to our writing pad. Basically, let me comment this one out. Let me come back to our writing pad. So yeah, let me turn this off. So I hope now you have understood what is def param. Okay, it cannot be modified. Like no, so not def param. Sorry, what is local parameter? It cannot be modified using def param. But local parameter values cannot be overwritten, ensuring remain constant. So it will always remain constant, not even with def param. Not even with def param. We cannot change the parameters with def param. Okay, so like these are all parameter use case. I've already explained you what is this parameter, what are the advantages of parameter, that also I have explained to you. So I don't think like I have to explain much things here. The last one topic is left, compiler derivatives. Okay, so if you have seen, like if I go back to the code again, if you have seen in the code, sometimes I'm writing at this, right, colon this, time scale this, then not colon, this is like I also don't know what is this symbol called, hash, like this dash, some top dash, include parameters dot v. What do they mean? Like here also sometimes I don't have called anything here, but what do these mean? That is what I will just explain. Not that important, but like we should know everything, right? So I will explain this here. So here these are known as compiler derivatives. Compiler derivatives in Verilog provide mechanism for pre-processing, inclusion and conditional compilations. These derivatives enhance modularity and maintainability and reusability. This dash define, right, directive is used to define text and macros and constants. It is similar to hash define in C. So is it here? Have I used it? I have not used it actually. But like if I write here, right, dash define macro name, value or text, then if I have to try to display that, it will be used. So I will just explain, I will just show you. Let me turn on the Verilog. Okay, and let me use this parameter only. Inside this let me use this last one, ALU only. Okay, all the parameter will be easier for me to explain. So let me define a macro here. Okay, let me define a macro here. So if I define a macro, it will be okay. So I have made the required changes. Basically, if you want to define any macro, right, you can define it here. Okay, and it's macro, and this will be accessible to the whole code, to the whole Verilog code. This will be accessible. Okay, this will be accessible to the whole Verilog code. So now, if I just want to display this macro, right, how you can access the macro? You have to first of all put this symbol dash, like on the left of your number keyboard, 1, the symbol will be there. Just press that, you will get this symbol. Okay, then you write the name of the macro and it will automatically replace with 32. This has to be constant, this cannot be a variable. Okay, and you cannot change this. Okay, so that is how you access a macro. This can be accessed in this module as well. Okay, it will be accessed, it is like a global variable, it can be accessed from anywhere. So that was one, define. You can write a string as well. Okay, so let's write define. Let me copy this only and paste this, Anish macro name. Okay, and let me write Anish Verilog. Okay, so now if I want to print this, how can I print this? Again, you have to print it here only. Okay, so now I will add another statement, display statement, macro ni. Again, you have to use that same statement, but remember the format specifier now is a string. Okay, so you have to write S. That is very important. S is for string. Okay, so you can see Anish Verilog is getting printed. No problems with that. Just be careful. If you write here D, right, it will just show the ASCII equivalent of whatever the string I have written. Okay, it is just showing a number. This is the ASCII equivalent that I discussed while discussing about string. It will just show you the ASCII equivalent. Okay, just be careful about the format specifier. Percentage S is for string. Okay, so that is only what I wanted to discuss about the compiler derivatives. Let me come back to the code, to the writing part. Basically, this is how you define a macro. You can write a string or anything similar to slash define on C. So avoids let's say I want to use this Anish macro, right, multiple times. Here, multiple times I have to write 32. Sometimes I will make a typo. If I write this Anish macro, right, everywhere I can see Anish macro, and if I change Anish macro here, everywhere else it will get changed. I don't have to write 32 multiple times and then change everywhere. Okay, that is the advantage. Similar as parameters. Okay, now next is include derivative. Include derivative, you see here I have include. So what does include derivative means? Include derivative basically means include this file in this test bench. So now if I whatever modules I call, right, parameters, this is defined here, but I am able to call it here because Verilog understands parameters. Now Verilog will search for the definition of the parameter. Where is parameters defined? Parameters is defined inside the file parameters.v. That's why this is very important. If I don't include this, right, if I don't include this and then try to run my code, it will throw out error because it will say these modules were missing parameters. Verilog doesn't understand where is the module parameter, what is the definition of the module parameter. If I include this, then Verilog understands, okay, look, go in the parameters file and search for this definition of the module parameter. It says, okay, here the definition of the module parameter is given, so it does not throw any error. Okay, that is the use case for this include derivative. Okay, and then there is like type derivative, time scale is used for denoting time, and then there is if not def. Okay, so this you don't have to, this is not that important. Conditional like another macro is there, this one. Okay, this macro that if it is defined, checks if the macro is defined and checks if the macro is not defined. So if end def, right, means if the macro is not defined, then it will do that. Okay, so let's say I am here and I am defining a macro. So first what I will do is I will do this. So first here the macro has been defined. If the macro has been defined, and if the macro has been defined, then only I will do this. Okay, so sorry, I am not showing you the notepad. So like I will not show you the code, just it is same thing only. I have defined a macro named feature x. Now this, right, this statement, it checks if the macro is defined. If the macro is defined, then it will do the following statement. If it is not defined, then it will do the else. Okay, I hope you understood this. Okay, we will not generally use this, but still I have to explain you everything. That's why that is what if defined is, and if not defined, if it is not defined, it will just be the opposite. Okay, time scale I have already explained, and compiler derivatives, these are like all the use cases and the definitions written. So at the we have reached the end of today's lecture basically. So now what I wanted to leave you with is the questions. So whatever we have learned, so these are all from exercise questions from the book Verilog HDL by Samir Palnitkar sir. So try to solve all the questions, try to do it by yourself, don't see the solutions. Okay, and in the next lecture we'll solve all these questions. So pause the video, try to solve it all by yourself. This is the assignment for today's lecture. So thank you for watching, and I will see you in the next lecture. Until then, happy learning. If you learned a lot of new things, make sure to hit the like button and put a comment below in this video and in the first video of the playlist, so that other students can realize and continue with this playlist. Thank you for watching, and I hope to see you in the next video.